Okay. Yeah. Now it has many applications because currently I am working on a ant, which is basically its behavior. So in its collective behavior, if you write a simple model of that animal beings, the ant, it is available in this West Bengal. So we are basically seeing their various collective behavior. So I think that is also counted as zoology, as I am collaborating with some of the in the biological department of the Isaac Kolkata. So it is good to see you. But as I am from physics background, so I am actually learning little bit of the collective behavior of the ants and zoology part. Interesting subject. Hmm. 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 Ah, see. Okay. So, so let's start then. Uh, so, what do you mean by the prediction? Means, do you know about, means in science we usually use the term that we want to predict something. Do you know what does this prediction? What do you mean by this prediction? Means if some layman asks you, can you predict something? What do you mean by prediction? Because suppose can you huh, huh, hmm, 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 hmm. Right, right. Actually, yeah, that's the thing. But so here that is true that predicting something means if I know the state of something at time t, we want to know the state of that things at t plus some another time capital T. So this is called prediction. Now, uh, we want to see how these meanings of the predictions means you can predict many things from a system, but in the from the perspective of a physicist, so the meaning of the prediction changed a lot from its beginning. Now, means I gonna I gonna simply say physics means since chaos is an subject is in the means it's remain in the many, it can be study of many subjects. So I only telling you the from the perspective of the physicist. So uh, physics itself a experimental subject, and its experimental results will be the theoretical prediction, as you said, the theoretical predictions. The theoretical prediction will be verified from the experiment. So that physics do. And physics is little bit different from other sciences because the role of mathematics is crucial in physics. So in the physics, so in the theory of physics, we actually we actually conclude something or actually predict something only by mathematical logic. So that's why physics is different. Whenever we want to say some prediction, we'll say prediction means we will uh, predict that things only from the mathematical logic, nothing more than that. Now, if I go at the time when the physics was born, then the what is the definition of the what is the definition of the word prediction. At first it may sound naive that it is obvious what is the meaning of the prediction, but as it is very important in science to define the quantity you want to work with. So let's see how does the Newton and Laplace in that era, how they thought what the prediction was. So before that, let me introduce what is the state of a system. State of a system. Now, state of a system can be anything. Suppose that as you are listening this lecture, so you may be sitting in front of a laptop or maybe a mobile. That will be the state of yours at this time. But at the later time when the lecture will be finished at the time 12 p.m., you will be somewhere else. So I can define your state in the perspective of this lecture. So whether you are listening this, whether you are in front of a laptop or not, I can say that's a state of you. So that is a state. But in the how the Newton or in the classical how the state is defined in the classical mechanics. So this is the general view of the state. State can be anything, but in the case of physics, when we are dealing with the state, we only dealing with the physical aspect of the state. Suppose that the temperature of the body or the position of the body or something like that. So or velocity of that particle. So we only want to state means we only want to mean that things in terms of physics. But we will later on see in this code that we will see the total number of individual in a population can also be the state of that system, and we will make that to see the chaotic outcome from a simplistic equation. We will derive that equation from a population model. So before that, let's focus on the what the prediction means. So in classical physics, if we go in the era of classical physics, in the classical physics, the state means basically, it's suppose there is a particle in three-dimensional space. So it has three coordinate x1, x2, x3 or x, y, z. So three coordinate x, y, z, and suppose it is moving with some velocity, then the velocity vx, velocity along x direction, velocity along y direction, and velocity along z direction, will these six things actually specify the state of this particle. So this is in classical physics, this is called state. And again I am saying, suppose a population in the population biology. So in the population biology, what will be the state? Suppose there is a population whose size is n, so this n will be the state of the system. Now in the classical physics, the prediction means if I know the initial condition, or maybe I know at initial time, suppose I know the state ti, suppose at t0, t equal to suppose 11 pm, suppose from that example. So I know the state of the state of an individual who is listening this lecture. I know that state in front of a camera, in front of a laptop. So I know that state. So at t equal to 0, I know the state. So I know the vector x or the position coordinate x, y, z, or vx, vy, vz. Now, if I do experiment, and after, suppose I am going to take this lecture multiple times, so this could be thought possibly as experiment. So if I do this experiment multiple times, and after when the class is finished, suppose at t plus t time class is finished, your coordinate or your state will be something like x prime, y prime, z prime, or vx prime, vy prime, vz prime. So this will be your state. Now, if from only from mathematical perspective, if someone gives me this state only, if from the mathematical logic I can predict, I can reproduce this result, if I can reproduce from this result only by mathematical logic to predict these. So if I can reproduce this exact state, I will say this is my prediction. So prediction means only using by mathematical logic, if I can predict the result which I am observing by doing the experiment multiple times. So if the mathematical logic reproduce the final state, if from only initial conditions, and if the derived final condition matches with the experiment, we will call this mathematical procedure is the prediction of that system. Okay, that is the classical definition. I can exactly predict the position coordinate and the velocity coordinate of any particle. So to do that, what Newton did? Newton write an equation. That equation is dp dt is fx. So don't worry, as many of in this course are not from the physics or mathematical background, so don't worry about this. This basically says at what rate d dt, means at what rate momentum is changing or something, p, the not momentum, not using the word momentum, the quantity p, I define some quantity, and at what rate the p is changing, and it will depend on the position coordinate. Now, and what is the p? How I define the p? Now, dx dt, if m is the mass of that particle and if x is the coordinate, then dx dt is p. So that's how Newton write the equation. Dx dt means the rate of change or the velocity, mass into velocity equal to momentum. So that's how Newton write an equation. Now this equation can predict the future. What is that this equation can predict the future. So if you, in the classical regime, if you experiment multiple times, and if you know initial conditions, suppose you know x0, y0, z0 and vx, vy, vz, then from this equation you can predict the final state at any time. So that means this equation has predictability, or this equation can predict the future. In the Newtonian era, this means the prediction. Now, something remarkable happened in this time that I have pointed out in previous lecture also, that in this time, uh, Newton, why the Newton was so much successful, because he explains uh, his laws of the force or gravitation, clearly explains that the dynamics which are following in this earth, that is also followed by the heavenly objects, such as moon and sun. So all the things that are in the nature, it is not a matter whether it is in the earth or it is in the above the sky. No matter what it is position is, all the things will follow the Newtonian law. So that is the remarkable thing. But another thing happens in the 19th century, that means in the 1830s. So a mathematician came, that is, his name is Poincare. So he was studying three body problem by using, this equation is for single particle. Since you see, single particle at a time only has one momentum and one position coordinate, because a single particle cannot occupy two positions simultaneously. So it has a single, at a time t, it has a single coordinate and single momentum, so it is single particle. Now you can write this force equation for multiple particle also. For the multiple particle, what you need, so if you have multiple particle, so if you multiple particle, the multiple, since multiple particle cannot occupy a single same space, so that means suppose you have a three particles, so three particles should have three position x, y, suppose x1, x2 and x3, and it could have the three different velocity, p1, p2, p3, or it could have same velocity, but the position could not be same, because if there is some particle and it has some mass, so another particle cannot occupy the same space. So that's it. So that means our force and this equation will be much more difficult. Means I write the equation in 1D, and here I have to write a equation in 3D. Now why I am interested in this, because there is a in the history of chaos, the three body problem plays a significant role, because at the 1800, I think 1860s or 1830s, Poincare, a great mathematician, studying the three body problem. Suppose there is the sun, earth and moon is there. Now here you will see there is a three body, so these have three coordinate, x1, it's suppose x2, and it will be x3, and its momentum will be p1, its momentum will be p2, its momentum will be p3. Now while he was studying this system, he found that the solution, or the solution means predicting the future at time t. If I know, suppose at t equal to 0 or some any time, suppose t equal to 10 am, I know I want to, suppose t equal to 10 am, I know this thing x1, x2, x3 and velocity. I want to predict what will be its velocity, suppose at 12 pm, that will be my solution, or that will be the prediction of the system. Now while he studying the system, wants to predict, and his main motivation was that whether or not our solar system is stable or not. You suppose that if our solar system is not stable, then at the some point he maybe thought that at the some point the solar system, the earth will be far apart from the sun and the moon also do so, then our system will not be stable, and this is very crucial for him. This is the crucial things that these since our Earth, Moon, and Sun is remain intact for at least million years. So that means uh, since why I am saying at least million years, because in my mind I recently read, you suppose that you can relate that ants are in the earth at least 100 million years. So that means I could possibly say that from millions, at least from 100 million years, they are intact in their position. These pointing out toward the thing that these three things, these three bodies, that sun, earth, and moon, is actually very stable things. Now, but while studying, he find an beautiful thing, which is beautiful because of our because it shows some chaos in the system, and since it is chaotic, it is very very hard for him to solve this equation. At least with very powerful computer also to solve this problem is also very hard. Now from these, what from this system, because this system now three body problems become chaotic, become chaotic. Now there is a important property of the chaos. What property? Now chaos means there is a dependence sensitive dependence of initial condition. Means if your initial condition is little bit means it's very, suppose that your if your initial condition is very, means it's not exactly x1 x2 x3, you don't know exact x1 x2 x3 at 10 a.m., but you know approximately x1 and approximate x2 and approximate x3. And since system is chaotic, it since it has a property, the sensitive dependence of the initial condition, the system will become, the system's prediction will not match at 12 ppm. The systems will be large, the predicting value, suppose okay, let me if your predicting value is xt and your actually the system is in the, suppose this is prediction value and it is originally the system is at xt, it will be, the difference will be very high, very large. So you cannot predict from this approximate initial condition to the final result theoretically. So this means your predictability was lost because of the sensual dependence of the initial condition. Now if one says no one could give the precise value of the initial condition, no, it is not actually possible. How much since whenever you want to measure, whenever you want to measure something, it has some finite precision. Now since it has finite precision, you can't go beyond that. So that means you can't put exact initial condition in a computer, since a computer has a limitation that I can only put a number with finite precision. So that means if I have a infinite precision, if I need infinite precision, I cannot also write that infinite precision number in a computer. So that means there is no way to give with certainty the exact initial condition. So that means this says that the predictability was lost. So in the terms of mathematics, you say that so this is called the so this is called the deterministic chaos. So this is called deterministic deterministic chaos. Why deterministic? Because we can know the equation of motion. In case here we know the gravitational equation is the governing law of this three body problem. So the system is deterministic. In principle, I have the equation. The why it is deterministic? The system is deterministic because we know the exact mathematical equation by using one can use it for prediction. But why it is chaos, and the second part is chaos. Why? Because to predict we forget altogether one thing. To predict we need initial condition, and this system has a sensitive dependence of the initial condition. This is sensitive on, this is very much sensitive on initial condition. That's why if I can't able to give a proper initial condition, my predictability also will be lost. So how? Let's see it in terms of mathematical term. So suppose suppose at t equal to 0, means at time t equal to 0, suppose my exact original state is t equal to 0 x0, but experimentally I can only go, it's very near, but I cannot tell you exact number x0. So I can tell you an approximate value x1 of this state. If this is state means suppose this is position of a particle, or you may think that suppose there is a large huge infinite, suppose there is a huge population, and by you are taking a survey, and while doing the survey you cannot tell exact number, because when you are telling exact number, maybe somewhere in the some part of the world there are individual born, or some individual die, so you cannot exactly tell what is the total number of individual at this moment in the earth. So suppose x0 is that number, and x1 is the approximate value, that while surveying and telling me some number, that maybe approximately at this time the total number of individuals in this earth which is actually available in the web, that is what, if you search in the web you will find some number. So what that number tell, that number will tell approximately what number of individuals are there in the earth in this moment. Means suppose in this moment we are starting the experiment. So that means x10 minus x00 is proportional to, means suppose since these are approximate value, so these two be very close. Suppose this is very close, suppose this very close means epsilon. In mathematics and physics, this number epsilon means very small. You see this, don't think this epsilon, suppose you see this is a very small number, that is epsilon. Now what chaos says, that these two at, suppose I know only this information, and actual state of the population is this, but I know this. Now using this x10, I want to predict what will be the outcome of at time t, at the, suppose at what month later what will be the state of the population. I want to predict that thing from that x1, and after predicting I will after 1 month I am going to observe what is the actual state of the population of the human population of the earth. So that difference If the system is chaotic, then the difference x1t minus x0t will be will be proportional to, or will be, we may write it, oh, equal to approximately equal to epsilon e to the power exponential t by tau. Now you see, when time increases, this my prediction and the actual state will become they are going far apart from each other. So how they are going far apart? So they are going far apart exponentially. And this is a beautiful, there is a beautiful thing is we can say from this expression. So you see, so epsilon, if I, you can expand this exponential. So exponential means 1 plus t by tau plus 1 by 2 factorial t square by tau square plus 1 by 3 factorial t cube by tau cube plus it continues infinitely. Now what is the importance of the tau? So Sopusachi, can you tell me what is the importance of the tau, since you are from the huh. Okay, so you see, suppose here you know one thing, that suppose you have a number which is less than 1. Suppose I have a number, suppose I have a number which is less than 1. Suppose x is less than 1, and suppose less than 1, less than 1. Suppose x equal to 0.5, and what it has a some property, because if it is less than 1, it has some property. Suppose what will be x square? X square will be 0.25, and you see that x square will be always lesser than 0.25. Now if you say x to the power 4, x to the power 4 is much, will be lesser than, or x cube. Suppose x cube will be 0.125. That is also lesser than, means x is higher than x square, is higher than x cube, is higher than x to the power 4, and it continues. So you see, if this number t by tau is less than 1, if t by tau is less than 1, what will happen? You see, this series is t by tau square, t by tau its cube, plus dot dot dot, it's mean it's t by tau to the power 4, t by tau to the power 5. As if t by tau is less than 1, we can surely say that this is much more higher than this, and this is much more higher than that. So this saying that if I include only this factor, this will contribute less than t by tau. Clear? So that means if t is less than tau, our error will not be much, because I know our error will be in the order of t by tau, which is less than 1. So our error will not contribute much more in the final prediction. Subhusachi, now you can understand what is the, why this t by tau is less than 1 is so important. Okay. Now it is means, that's why if the t by tau is less than 1, then I can ensure that I can predict the system, because I know then our error, that our predicted value and the actual value at time t is not very not far apart, because I know this this term is less than 1, all the term will be less than 1 now. So that means at if t equal to less than tau, we can predict predict the system approximately. But one thing will happen when t greater than tau. If t greater than tau, that is actually means t by tau will be greater than 1. If t by tau will be greater than 1, this thing will be changed, because if I assume a number suppose 2, t by tau is suppose 2, then t by tau is square is 4, and t by tau to the power cube is 8. So you can see that t by tau is less than t by tau square less than t by tau cube, and it goes on. So then if I focus in this equation, you see it is not remain in the order of 1, it become much more higher than 1. So if I add suppose t by t is 2, so 1 plus 2 plus 3, there is again 2 square means 4 by 2 4 5. So you see if the t by tau is greater than 1, then the difference will become huge. As I increase t a little bit, the difference between x1t and x0t, that my predicted value x1t and my actual value x0t, the difference is very high. So we cannot predict the x0t from my formula by using the initial condition x10. So that means my prediction only remain when t less than tau, and this is called the characteristic time, or you can see, I will in the later in the course I will show you how this correlation comes, how you can calculate t from their governing equations or governing law. So that's how a chaotic system, by in principle, due to the fact of the system is deterministic, you can only predict the system only for a only for a characteristic time tau. And if your experimental observation time is much more higher than that, you can't say anything about the system from your approximate initial condition, because theoretically your predicted value from math and your observing your value that is actual there means my theoretical calculation by using the current data of that human population, and if I calculate a math and I get a number, what will be the population size at 1 month later of the human population size at 1 month later, that number and actual number will differ so much that I can't say that my predicted value is actually prediction. It is not actually prediction, because these two is not matching at all. So that is happening here. But suppose that I can also using this equation by if I know the current birth rate and death rate of the total population, I can predict the total size of the population at suppose at the after 2 days what will be the total size of the population, that I can say so. So that will be the characteristic time tau. So that's it. Now if that is happening, so okay, so if that is happening, so if the predictability is lost, so now comes the question, now what you will say, what will the predict, now what is the meaning of the prediction now? What is the meaning? Prediction. Now see, as we have previously see in the Newtonian era, that the prediction means writing an equation. If I put initial condition, it will predict the future. So that will actually basically prediction. So to know the final state, but here you see, since we cannot, if system become chaotic, if we cannot give the initial condition properly, we cannot get the idea of the future state, even if I have the equations for the system. So now comes another perspective of this prediction, that is means there are these prediction, this perspective of prediction comes in the physics in three way. First is statistical physics. Statistical physics which relate the thermodynamics. To explain thermodynamics, from there is a from the microscopic, we actually need the statistical physics, and in the statistical physics the meaning of the prediction is not the same as the prediction of the Newtonian era. And the second is the quantum mechanics. Here also the prediction does not mean the same as we have discussed previously. Now third is the chaos, or it is say complex system. Complex system. So first two the statistical physics and quantum mechanics is out of the scope is this course, but in the third thing, the complex system, it's a single part, that chaos. We can study the chaos from we can learn the chaos and the meaning of the prediction from the chaos. Now as we see, the predictability was lost. Now what will be the prediction here? Now it says, can we say, now the prediction means, can we say probability, can we say at what probability, the state of the system will be x. So suppose if you can tell me the probability, what is the probability that if I know some initial condition, suppose from x0 I know that initial condition or near about, if I start from this near about condition, what is the probability that I will say that the population state will be that? What is that probability? So now you see that my prediction, definition of prediction changed from what is the exact state, what will be the exact state at time t, to what is the probability of achieving that state if I start from this near about initial condition. Now this is now the prediction, now the meaning of the prediction change. This is okay. Now if I say, so is there is a relation between this and that? Yes, obviously there is a relation, and it is very we means the strictness of the definition is loosened here, because you see, when I am saying that if I know initial condition x0, I can tell you what will be the final state. It is in Newtonian era. So that means if with probability equal to 1, means if there is some certain event, we say the probability associated with it is 1. So if I know with certainty, that means if the probability 1 of happening x0, I know with probability p equal to 1, the system will be there in the x equal to 1, and in other states about x2, x3, x4, x5, the probability of finding the particle in x5, x4 will be 0, and x3 will be 0. Now we loosen our the definition, the strictness of the definition, by saying that no, since we in the chaotic system we cannot say with certainty with p equal to 1, so p will be less than 1, with complete certainty we cannot exactly say the initial condition. We cannot also conclude, since it has it is such a sensitive dependence of the initial conditions, we cannot certainly say that its final state is x1. Rather its final state would be x1, would be x2, would be x3, would be x4, would be x5. But suppose that there is many things, but I know the probability of px1, what is the probability I could find the system in x1, what is the probability I could find the x2 and x3 and so on and so forth. So now our prediction shift from this value x1 to this probability. If I can predict the probability distribution, that what is the probability at px1, px2, p3, we can we can tell that the system has the predictability. So you see that what is the meaning of the prediction changed in when the we in the, in, when this physics evolved. Now you see, since we change the definition of the prediction, we can conclude many more things in the umbrella of physics. So that's it. So it has a so if the system become chaotic, so that's the one aspect. Now Subhusachi, is it clear that the two definition of the prediction, so how the prediction definition was changed? Huh. Hmm. Right, right, right. Huh. Right, exactly, 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 exactly. No, now that's the main thing. Now I want to okay. Let's see some, means there is a example. I am generating it is in Python. I will show you. So in the billiard board, if you suppose there is a board, or suppose something, there is a board, and suppose there is a two balls are there. Now if this table is frictionless and these are the perfectly reflecting surface, then if these two things doesn't have any collision, you will see a very smooth kind of dynamics. Let me show you, then it will be clearer. So let me show you. Okay, let's wait. Now we'll see. Ah, now you can you see the Subhudaji, that here the two in this is a billiard ball, this is a billiard table, and these four boundaries are perfectly reflecting boundary, and these two balls don't have any collision between them. Now we can see very regular kind of motion, that it has certain period, and it is roaming around inside this circle, and it will forever remain inside this region. And these balls, means this has a very periodic, they see very what I can say, that this has a some something, though they will not stop forever, they will moving and moving, there is no period, but this is called quasi periodic in the terms of physics. So but there is certain pattern of the system. Now you will be now can you say, means can you predict what will happen if I just simply add collision? So since you are not from physics background, let me tell you what the collision means. So in the collision means simple thing. Suppose this is two particles are there, they have same mass. Now if this particle is moving in this direction with velocity v and v1, and if this particle moves in this direction with v2, then after collision means if they collide in this way, if they collide in this way, then this is suppose m. Okay, this is m1, this is m2. Then after a collision, since they cannot go inside one another, so if it is elastic collision, then it says this m1 particle after collision will move in this direction, but will get the velocity of the particle of m2. This is suppose m2. So m1 will get the velocity. Suppose this is, previously it was moving in this direction with velocity v2. Now after collision, this m1 will move in this direction, but with the velocity v1 of the particle m2, and this m2 will move in this direction with velocity v2. So this is basically the law of the Newtonian law. So if you conserve, since it is I have assumed the elastic collision, so if you conserve the total energy and the total moment of the system, you will get this solution. So this is my system again. This is my system initial state, and this is the final state. This is the prediction, and in this prediction, it is predictable system from the Newtonian equation. You can predict that things. Now you can see I add one more complexity to the system, that now these two particle is not in the free space but in a billiard board, with there is a reflecting boundary condition everywhere in this board direction. Now I want to see, can I predict from the Newtonian equation? Let's see. Now let's see, can we predict? Now is it behavior is quite now you see the behavior of the particle is very chaotic, because there is chaos. So from this simple if I add simple collision and simple four boundary of billiard board, so you see that the particle will move very erratically in the space. So you can see now you cannot predict the future state of this particle. If I start from little bit if I shift their initial condition very little, then also we can't predict the system, because you can see from here that it's the state of the system is become very much chaotic. And another property I want to notice, because that is a very basic property of the chaos from here, that is the transitivity. That you see that the trajectory of this particle or these two balls actually will travel in every open interval of this 2D table. So you see that sometimes it will move here, sometimes it will move here, here and there. So it is not like that it only remain in a particular area of this four-dimensional box. At some point of the time it will go if I say in this region, it will at some point it will come to this region also. So this property is called the transitivity, and we will mathematically prove that how the chaotic system will have the property of this chaos. And you see that when these particles become its trajectory become more chaotic, when you see when these two particles will collide with each other, you will see that it's the motion of these two particles will become very erratic. So that's it. So that's it for the today's class. Now if you have any question, you can ask me, or we can meet Monday. So in the next day I will show you how to write a population model, and from that population 1D model we will see that how the chaos will automatically come. So here you see, here is the equation is little bit different. This has a thing. So it can be met. So one thing I want to be mentioned here, that for three for okay, let me write it. So for for continuous equation you need at least, okay, let me since we don't know the what continuous equation is, let me, I will introduce these things in the next class. So if you have any question, you can ask me. Suppose you are you can we can end this meeting here. Huh, huh, huh. Okay. Transitivity means, suppose, let me, I will come upon these things. I will prove that thing, that what transitivity is and how I can prove the transitivity. So suppose there is a particle, that means, let me give an example from this. That's also. So that is the box. So transitivity, definition of the transitivity says, if you start from any initial condition, it says if the system has the transitivity property, that if you choose any random open interval in this 2D box, suppose any random interval, suppose here, if you choose random interval here, and it says if you wait enough, if the system has the transitivity, at the some point of the time it will come inside this box and it will go outside, but it is for with certainty it will come inside this box. It is called the transitivity. Is it clear? Uh, hmm, 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 hmm. Hmm. Ah. Hmm. Okay. 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 Monday. Yeah. Hmm.